Hey everyone, welcome to lecture 9.4. So we're finally going to do a hypothesis test. We've made it. All right, so we've got an idea of what null and alternative hypotheses are and how to construct them. We have an idea of what alpha means as a significance level. We have an idea of type 1 and type 2 errors. We've also discussed what distributions we're going to use in order to do our hypothesis test, right? So if we're doing the mean, we're testing about the mean, and our standard deviation for the population is known, we're going to use a z-test. If we're going to hypothesis test for the mean and this population standard deviation is unknown, we're going to use a t-test and we're going to use the sample standard deviation. And if we're going to do a hypothesis test for the proportion, we're going to use a z-test or a normal distribution. And we have some assumptions for each of those different scenarios. So the other critical thing here that we have to remember is that when we're doing our alternative hypothesis, that tells us whether we need to do a two-tailed or a one-tailed test. So we've got to keep in mind, are we doing a hypothesis test for mean or proportion? Do we or do we not know the population standard deviation? And is it going to be a two-tailed or a one-tailed test? So these are the three key things that we must keep in mind when we're performing our hypothesis tests. So the first few examples we're going to do here, they're all going to be very similar. And I'm just going to kind of change a couple of key things. The numbers may change, but the types of information we have is really going to be what changes what test we use. So let's go ahead and get started on this first example. San Jacinto College reports that the mean GPA for full-time students has a mean of 2.8 and a standard deviation of 0.65. We would like to test whether the GPA for full-time students is different than 2.8. We take a simple random sample of 100 full-time San Jacinto College students and found that the sample mean is 2.71. So first, let's state the random variable. The random variable here represents what the outcome of a single data point would be. So the random variable X is the GPA of a full-time San Jacinto student. Next, we need to check the assumptions. So let's get a context for this problem. First, we're doing a hypothesis test for the mean. Second, we are given the population standard deviation. And third, we're going to use a two-tailed test. So the first two things are pretty straightforward, right? It tells us that we want to test about the mean, so that's how I got that part. It's telling us that the population standard deviation is 0.65, so that's how I got my second statement. But how did I know it was a two-tailed test? Well, remember that when you want to test that something is different than, your alternative hypothesis is not equal to, and that gives us a two-tailed test. So we'll revisit that in a second on step 3. So first, let's check the assumptions. Do we have a simple random sample from the population? Yes, it says it explicitly in the problem. It says we take a simple random sample. Next, we either need to know that the population is approximately normally distributed, or we need to have a sample size that it's at least 30. So we're not told that the population is approximately normally distributed, but we are taking a simple random sample of 100 full-time San Jacinto College students. So I've met my assumption for 2B. And then lastly, we need to check whether or not we know the standard deviation for the population. Again, we do, it's in the problem, we just discussed that. So that's going to tell us that we're going to use a z-test. So the next thing we want to do is we want to state the null and alternative hypothesis. So San Jacinto College is telling us that the mean is 2.8. We would like to test whether the GPA is different than that. So remember that what you want to show, what you want to test is always going to be your alternative hypothesis. So our alternative hypothesis is that mu does not equal 2.8 And the null hypothesis is that mu is equal to 2.8. So remember from the early part of this chapter, when we have our alternative as mu not equal to, or in some cases, if p was not equal to, then this is going to give us a two-tailed test. So the next thing we want to do is we want to establish a level of significance. So in 9.2, when we talked about the type 1 error, we said that the probability of a type 1 error was equal to this Greek symbol alpha. And alpha is also called the level of significance. We, as the statisticians, we get to decide what level of alpha is appropriate. And so we had some guidelines there on how to choose alpha based on whether or not a type 1 error was worse or a type 2 error was worse, or if type 1 and type 2 were equally bad or equally benign. So in this problem, I'm just going to arbitrarily choose alpha equals 0.10, because I would say that a type 1 error and a type 2 error, it doesn't really matter. It could have gone 0.05 as was another suggestion, but I don't think there's a lot of consequences to this average GPA problem. So the next thing we want to do is we want to compute the probability that our sample mean occurs, assuming that the null hypothesis is true. And this is going to give us what's called a p-value. Once we have our p-value, we're going to make our decision based on p. If p is smaller than or equal to alpha, then we're going to reject the null hypothesis. If p is greater than alpha, then we're going to fail to reject the null hypothesis. So let's see how this works. You're going to want to go and download or open up your Excel sheet for chapter 9. So once you have your Excel sheet open for chapter 9, which you can get on Mom in the usual place, then you're going to want to start entering in your values. So notice that we are using a z-test. And in Excel, we have an option z-test for the mean, we have t-test for the mean, and we have z-test for proportion. So since we know the population standard deviation, we want to use a t-test. And we want to make sure to use the z-test for the mean, not the z-test for the proportion. All right, so for z-test for the mean, we need to enter in mu. So mu comes from the null hypothesis. So the mu given by the null hypothesis is 2.8. We need to enter in our X bar, which is going to be our sample mean. So remember, we're sampling 100 students, and we found the mean was 2.71. Next, we need to tell Excel what is the population standard deviation. That was 0.65 given in the problem. N is our sample size, 100 given in the problem. And then alpha is our significance level. So in step 4, it says establish a level of significance. So here we chose alpha was equal to 0.10. And so now that we have this, our table will kind of fill out with all of these values. So let's look at what all of these values mean and figure out how we're going to interpret this information so that we can decide whether or not we want to reject the null or fail to reject the null. All right, so I've copied and pasted our output into our notes. So let's kind of just parse through this one by one. We know what mu, X bar, sigma, N, and alpha are because we just input them in. We took them from the problem. But now we have this value for a test statistic Z. So let's see if we can kind of put together what all of this stuff means. So remember, when we're doing a hypothesis test, we are assuming that the null hypothesis is true, meaning that we're going to go ahead and assume that the mean is actually 2.8. And so this is our sampling distribution, where remember that the sampling distribution has the same mean as the population itself. So that's kind of the trick to making, at least justifying this in your head if that's something you wanted to do. So now relative to the mean as stated in the null hypothesis, where do we fall? Where is 2.71? Well, what we see here is that we have a test statistic. And the test statistic tells us this is how far away X bar is from the mean. And again, this is the assumed mean, mu. And so it's telling us that the test statistic Z equals negative 1.385. So that's saying that I'm going to go 1.385 standard deviations to the left as it's negative. And that's going to be how far away my X bar is from mu. So here I'm going to have X bar equals 2.71. And the question really is this far enough away that we would consider it to be unlikely? And by unlikely, I mean unlikely to happen by chance. If it is, then we're going to go ahead and say, well, that's such a rare occurrence to be that far away. So probably what's really going on is that your mu is wrong. But how do we determine whether or not it's too far away? Well, the answer to that question lies within alpha. So the significance level alpha is 0.1. And remember that we are doing a two-tailed test. So for a two-tailed test, we want to split alpha equally on both sides. So we want to have equal area, equal rejection regions on both sides. That's what it means really to be a two-tailed test. So here we have a rejection region. And it is equal to, remember, if we're splitting it equally on both sides, it's going to be 0.05. So this area here is 0.05. And then I'm also going to have that same yet equal rejection region on the right side and the right tails. And so 0.05 is also the area of this right tail. So you can see together that if I added up these two rejection regions, the area would be 0.05 plus 0.05, which gives me 0.10, which is exactly the alpha that we had given to Excel when we started the problem, when we started the test. So if X bar had fallen into this rejection region, we would have rejected the null hypothesis, but it didn't. It didn't fall far enough away from the mean mu, from the null hypothesis, that gave us enough, air quotes, proof, enough evidence that mu was wrong. So since X bar does not fall within the rejection region, we fail to reject the null hypothesis. But there's actually a little bit of an easier way to make this decision. And instead of having to draw out a picture and figuring out, okay, well, what would X bar have to be to fall into the rejection region and blah, 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 blah. What I'm really going to look at is the p-value. So remember that we're doing a two-tailed test. So every time you plug this into Excel, you're going to get a p-value for a left tail, a p-value for a right tail, and a p-value for a two-tail. So it's up to you to decide which p-value am I looking at. So we know that we have a two-tailed test. So we want to look at our p-value for two-tailed. And our p-value is 0.1662. And in fact, what this p-value is telling us, it's really telling us this. Let me see if we can draw this nicely. Your p-value is really telling you what is this area right here. But when you have a two-tailed test, you have to mimic it on the other side. This is not neat. You don't need to know how this works in order to make the decision. But if you want to know how it works, this is what's going on. So the p-value is telling you the area. What is the probability that another sample would have a sample mean that's even further away from you, right? So the probability of this shaded region that's your p-value, and it was 0.1662. So if your area is larger, then that means that you're actually closer to the mean, right? So the closer my X bar is to the mean, we can see that I'm going to have more and more area in the tails. So when my p-value is larger than alpha, then my X bar must not be in the rejection region. And that's how we come to this summary here. If p is less than or equal to alpha, then we reject the null hypothesis. This would mean that X bar fell in the rejection region. And if p was greater than alpha, then we would fail to reject the null hypothesis. This would mean that X bar did not fall within the rejection region. So that's really all you want to do. You figure out what your rejection region is, and then you look at X bar and you're like, am I in the rejection region? Am I not in the rejection region? If I am, then I'm going to reject. If I'm not, then I'm not going to reject. And this p-value helps you determine whether or not X bar is in the rejection region. So for us, we have that our p-value for our two-tailed test is 0.1662. We know alpha is 0.10. So here, since p is greater than alpha, right? Certainly, if we write alpha like this, it kind of makes more sense to say 1662 is bigger than 1000. So since p is greater than alpha, and let's write it as a full statement, we fail to reject. What's the null hypothesis? We fail to reject what? We fail to reject the claim, because remember, a hypothesis is really kind of a claim that the mean GPA for full-time San Jacinto College students is 2.8. So remember, when we fail to reject a null hypothesis, we're not confirming the null hypothesis. We're just saying I don't not believe you. Like my data doesn't support that you're wrong. So I can't say that you're wrong. So let's try to do another example, a very, very similar problem. It's still going to be Sanjak, it's still going to be full-time students, it's still going to be the mean is 2.8, but let's change up some information. Let's take away the fact that we know the standard deviation. That's going to change what test we use, right? So when the population standard deviation is known, we're going to use our z-test, our normal distribution. When the standard deviation for the population is unknown, we have to rely on our sample standard deviation. And in that case, we're going to use our students' t-distribution. I would like to warn that there are lots and lots of very good tutorials and videos out there on the web that will say things like, well, if your n is bigger than or equal to 30, just go ahead and use the normal distribution because they're about the same anyway. And that is true. As n increases, the more closely the student's t-distribution becomes the normal distribution. But we don't need to rely on these kind of like hacks because we have computers and we have Excel that's going to compute it exactly for us. So I feel like using an approximation, using the normal distribution, even with the sample standard deviation, is justifiable if you are a person that doesn't want to have a lot of paper tables around or whatever, but we don't have those problems. So let's just go ahead and be precise. All right, so again, sounds familiar, right? San Jacinto College reports that the mean GPA for full-time students is approximately normally distributed with a mean of 2.8. We would like to test whether the GPA for full-time students is different than 2.8. We take a simple random sample of 25 full-time San Jacinto College students and found that the sample mean is 2.5 and the sample standard deviation is 0.7. So we've got a couple different things going on, but the main difference, the really important difference here, at least in my opinion, is that we went from knowing the population standard deviation to not knowing it. So we're going to go from a normal distribution to a student's t-distribution. All right, so the random variable x is the same as before. It's the GPA of a full-time San Jacinto student. But now let's check our assumptions. This time we're going to be, if you look at part C, population standard deviation is unknown. So we're using a t-test. Okay, that's important. We know we're using a simple random sample because it says so in the problem. And then for B, population is approximately normally distributed or n is greater than or equal to 30. Well, our sample size has changed. Before it was 100 and we weren't told that the population was approximately normal. In this version of the example, we are told that it's approximately the normal, but our sample size is now 25. But we still have our bases covered because we just need one of them to be true, like be approximately normal or have a big sample. Sometimes it'll be both. All right, we've got our null and alternative hypotheses. Hasn't changed. We're still doing mu not equal to 2.8 as our alternative, which means that we're using the two-tailed test. We're still going to use our alpha equals 0.1 for our level of significance. You might see this written as use alpha equals 10% or test at a 10% level of significance. Those all mean the same things. When you're entering it into Excel, make sure your alpha is a decimal. So if it's given to you in a percent, convert it to a decimal. All right, so let's compute the probability that our sample mean occurs, assuming that the null hypothesis is true. And we're going to do this to find our p-value. All right, so here we go. We want to create space so that we can use our Excel. But what we need to do is be careful here and go over to the tab that says t-test for the mean. So again, we don't know the population standard deviation. So we're going to use a student's t-distribution. So make sure you're going to the t-test for the mean. All righty, so let's clear this out and see what happens. Okay, so first we want to put in our mu, and our mu comes from our null hypothesis, right? So that's still 2.8. We want to put in our x bar, that comes from our sample. So let's see what it says. We take a simple random sample of 25 full-time Sanjak students and found that the sample mean is 2.5. Okay, 2.5. We need our sample standard deviation. And found that the sample mean is 2.5 and the sample standard deviation is 0.7. So 0.7. Okay, we need to know our sample size, and that's in the problem too. So we take a simple random sample of 25 full-time students. So 25 is our sample. And then alpha, where does it give me alpha? Well, not in the problem, so let's keep reading. Step 4, establish a level of significance. 0.1, huzzah. So now again, we can see that we have all this output. And if you're wondering what this big table is at the bottom, we will find out soon. So, all right, so let's take a screen grab of this and place it into our work so we can kind of digest what all of it means. All right, so remember that we are assuming the null hypothesis is true, which means that our mean we're assuming is 2.8. And we want to know how far away is my sample mean away from mu? And moreover, is it so far away that I really can't even believe what you're telling me about mu? So let's see how far away it is. Well, our sample mean is going to be here, 2.5. And you're probably wondering, how do I know where to put this? And the answer is, I'm a big fat cheater and I do these problems before I record my videos. So let's see, how far away, what does this test statistic tell me? How far away is X bar from mu? It's 2.1429 standard deviations to the left. Right, so if our mean is there, then this is telling me that I'm 2.1429 standard deviations away. And if you're wondering, you're like, hey lady, I thought the standard deviation was 0.7. So if you were 2.14 standard deviations away, you'd have to be like more like about 1.5 GPA points away. Remember that the sample standard deviation it's really not quite that. So you have to think about your old friend standard error, right? So the standard deviation for the sampling distribution isn't S, it's S over the square root of N. So let's look at that really quickly. So if S was 0.7 and N was 25, then this would be 0.7 over 5. And that's going to give us 0.14. Well, if I'm negative, or rather I should say to the left, if I'm left of mu by 2.14, so let's check it out. 2.1429 times 0.14, that's my standard deviation for this distribution, for this t distribution. That is going to give me 0.3. Well, if I'm left by 0.3, that's going to be 2.8 minus 0.3. Guess what that is? That's 2.5. That's X bar. So that's what I mean when I say I'm 2.1429 standard deviations away and on the left. It's again, it's not the sample standard deviation because that's not the standard deviation for this distribution. The standard deviation for this distribution is S over root N. It's our sampling distribution. Anyway, in case you missed that in chapter 8, good times. All right, what were we doing? Hypothesis test. So I'm 2.1429 standard deviations away from mu. Is that so far away that I would think, man, I think they're lying to me about this mu being 2.8 business? Well, how can we decide that? We've got to look at what our rejection region is. And so we can really think about it as we did before. You've got a rejection region. And actually our rejection region ends up being here. So I think that this Excel sheet, it's not clear what your rejection region is relative to X bar. So I'm kind of giving us the advantage of foresight. But I really, more than anything, am just trying to drive the point home that if X bar lands in the rejection region, then you really need to be rejecting your null hypothesis. Okay, so again, we have our area here. It's half of alpha, it equals 0.05. And same here, this is 0.05. Let's look at what would happen if we just took the tails that were beyond where X bar is. If I just looked at these tails here, right? And if I went, let's say I went on the other side, I went 0.3 down, let's say I went 0.3 up. What if I was over here at 3.1? A little symmetry for your day. This area of this yellow region, so remember this yellow region here, this area. This is your p-value. And we have two-tailed test. So the area of this region is equal to 0.0425. The area of our rejection region is bigger than it. So it's got to contain X bar. That's really what's going on. I don't know like a priori what value this this orange region ends at. I just know that if I were to cut off my tails at where X bar is, then I would be having a smaller area than if I were to cut off my tails at where my significance level is. So geometrically, spatially, whatever, X bar has to be in the rejection region. So if that spatially makes sense to you, awesome. If that makes no sense and you're just hearing noises at this point, that's also okay, because we have this handy dandy trick. If P is less than or equal to alpha, we'll reject. If P is greater than alpha, we will fail to reject. So we have our P value is 0.0425. And our alpha is 0.10. So we have that P is less than alpha. And in fact, sorry, it should be less than or equal to, but it doesn't really matter because it's significantly smaller. So since P is less than or equal to alpha, we are going to reject the null hypothesis, H naught. So if I were to write this nicely, I would say we reject the claim that the mean GPA for full-time students at San Jacinto College is 2.8. All right, let's look at a different type of example where we're going to be talking about a one-tailed hypothesis test. So this is really going to change things a bit. Oh my gosh, I never want to read this sentence again. San Jacinto College reports that the mean GPA for full-time students is approximately normally distributed with a mean of 2.8. We would like to test whether the GPA for full-time students is higher than 2.8. Yay, we have something a little bit different now. We take a simple random sample of 50 full-time SanJack students and found that the mean sample is 2.9 and the sample standard deviation is 0.17. So right off the bat, I'm testing for the mean, and I'm given the sample standard deviation. So this puts me in T land, T test world. All right, so again, the random variable, step one, it's still random variable X is the GPA of a full-time San Jacinto student. Same. Let's check the assumptions. So this is going to be the assumptions for a t-test, right? So we're using a simple random sample. Yes, it said so in the problem, so I believe it. Plus I wrote it, so I know I'm lying, but let's just go with it. Okay. B, population is approximately normally distributed, or our sample size is 30 or bigger. In this case, we actually have both. We're told that the population is approximately normally distributed, and we also have a sample size of 50. So we're good on both fronts. And then the last part is our population standard deviation is unknown. So again, reinforcing the idea that we need to be using a t-test for the mean. So let's state our alternative hypothesis. So remember that our alternative hypothesis is the thing that we want to show, or the thing that we want to test, the thing that we would like to be able to claim at the end. Kind of, maybe I'll take that back, whatever. So we would like to test whether the GPA for full-time students is higher than 2.8. That's what the problem says. So our alternative hypothesis is going to be mu greater than 2.8. And so this tells me that we are having a right-tailed test. Our null hypothesis is the same. It's the claim that San Jacinto is making that that the mean GPA for full-time San Jac students is 2.8. We're going to establish a level of significance. It's still 10% or 0.1, fine. So step 5, compute the probability that your sample mean occurs, assuming that the null hypothesis is true. This is your p-value. So we're going to go back to Excel, crunch it out, and digest the info. All right, so we're still doing t-test for the mean. And our mean is still 2.8 from the null hypothesis. So remember, this all really hinges on the fact that you're assuming the null hypothesis is true, which means that I need to put 2.8 in as the mean. Then I need to give it my X bar. So when we took our sample, we found that the sample mean was 2.9. So we need to change this to 2.9. Do I have my sample standard deviation? Yes, it was 0.17. So let's change that. My sample size is 50, not 25. So change that. My alpha didn't change. It's still 0.1, or I could say 10%. So now let's go ahead and grab this, throw it into our notes, and pick it apart. All right, so we have the assumption that mu is 2.8. I'm going to erase these because they get in my way. We still have our assumption that mu is equal to 2.8. Let's do this first. Let's start with the significance level just to kind of change things up. So we're doing a right-tailed test. So basically what's going to happen here is we're going to have 10% of area on the right. So this is our rejection region. The area equals alpha, and it equals 0.1. So the whole area of this right tail is equal to 0.1. Before, we had to split up our area equally into the two tails, which is how we got 0.05 and 0.05. But now all of our area is going to be to the right. And what we want to do is we want to look at where our X bar lands. So I actually don't really, well, actually I do. Okay. So the test statistic T, remember that this tells me how far away not me, it tells me that X bar is, I'm just going to call it 4.16. Maybe I won't. OCD won't allow it. It tells me that X bar is 4.1595 standard deviations above, because it's positive, above the mean, which is assumed. That's really, really far. So we know that the overwhelming majority of our data is going to fall within 3 standard deviations. So if I'm 4 standard deviations away from the mean, I'm probably like way out here, if not more. So this is 4.1595 standard deviations. And again, that's not the standard deviation 0.17. That's the standard deviation 0.17 divided by the square root of 50, the standard deviation of this sampling distribution that we're using. And basically what that tells me is that X bar is here. So we can see that X bar falls into this rejection region. But the other thing that tells me that X bar falls into this rejection region is the fact that the probability, maybe let's look at it this way. The probability that X bar is bigger than 2.9 equals a really small area. It's equal to 0.0001. That's what that p-value is telling you. So now we kind of had to switch it up. We need to make sure that we're looking at our p-value for a right-tailed test. So since this area is smaller, we know that that puts X bar in the rejection region. That's, again, the whole idea behind, if p is smaller than or equal to alpha, then this means that, of course, X bar has to fall within the rejection region. And if p is bigger than alpha, then that would mean that X bar falls outside of the rejection region. So that's where we get this rule from. So, all right, so our p-value, so now we can just go ahead and conclude. So we know that p is less than or equal to alpha, right? Because we had 0.0001 is less than 0.1000. That's like saying $1 is less than $1,000, and absolutely it is, I would know it. So we reject the claim that the mean GPA for full-time San Jacinto college students is 2.8. All right, so we have one more GPA example, which in hindsight, I really regret this, but I think it's good to illuminate the subtle differences. And then I promise no more GPA talk. So San Jacinto College reports that the mean GPA for full-time students is approximately normally distributed with a mean of 2.8 and a standard deviation of 0.45. So right away, I'm like, boom, I know this, I know the population standard deviation, which then triggers in my mind, I'm like, oh, I'm going to use a t-test. I'm going to use normal distribution. Keep that in mind. Next, we would like to test whether the GPA for full-time students is lower than 2.8. So we take a simple random sample of 46 full-time SanJack students and found that the sample mean is 2.7. So the random variable is the same. Let's check the assumptions. We know we're using a z-test. So we need to check that we know our population standard deviation? Yes, we do. It is equal to 0.45. Am I using a simple random sample? Yes, I am. Is my population either approximately normal or is my sample at least 30? Yes and yes, they're actually both true in this case. So now I want to state my null and alternative hypotheses. So again, the null is still mu equals 2.8. But now my alternative hypothesis is that mu is less than, because I think, and I want to show, and I'm going to test that the mean GPA is actually lower than, less than. So this is a left-tailed test. Remember that left-tailed, right-tailed, two-tailed, that comes from the structure of your alternative hypothesis. All right, establish a level of significance, 10%. So now we're going to go ahead and compute the probability that our sample mean occurs, assuming that the null hypothesis is true, and then we're going to get our p-value. So we want to make sure that we are in the tab for the z-test. Because remember, we're using our z-test because the standard deviation for the population is known. And if you ever get kind of tripped up on this, just look at the top of your Excel sheet. It says hypothesis testing for the mean when the population standard deviation is known. These types of descriptions also occur at the top of all of your Excel sheets. So remember that come final exam time. Alrighty, so mu is still 2.8. And X bar, what did we get for X bar? We got 2.7 for X bar, so let's switch that up. Our population standard deviation is 0.45. Okay. Our sample size is 46. Alpha is still 10. So I'm going to go ahead and grab this, throw it into our notes, and we will pick it apart. Okay, so remember, we're going to assume that the null hypothesis is true, because if we didn't, well, what would we really be doing with the hypothesis test, right? Because you want to say something like, hey, my sample is way far away from what it should be if the hypothesis that you said is true actually is true. That's really the whole setup here. So we are assuming that mu is still 2.8, which is officially my least favorite number of all time now. And our sample mean is 2.7. So how far away is 2.7 from mu? Well, that is our test statistic. It is telling me that X bar is 1.5 standard deviations away from mu. So each of these lines gives me a standard deviation. So I'm going to call it, let's call it about here. So X bar is 1.507 standard deviations below or left of the mean. Okay, so let's start with what's the area between here and here? What is this area? What is this area? So remember that we're doing a left-tailed test. This is our p-value. It's the area of the yellow region, right? The yellow shaded region. And we get that from here. So remember, it's up to us to decide, are we going to get the p-value for a left-tailed? Are we getting the p-value for a right-tailed? Or are we getting a p-value for a two-tailed? Because it always is going to give us all three. So we need to be judicious and understand which one we're grabbing. So we are doing left-tailed. So this area is equal to 0.0659. Our rejection region has an area of 0.10. So our rejection region is actually a little bit bigger than this. So again, we can just see at least spatially, if our rejection region has more area, then it must contain X bar. So we can see that X bar is in the rejection region. So that means that we're going to reject H naught. But again, if that's not really, if the graphical display of this information isn't really clicking with you, you don't have to go through such lengths. You can really just look at P and alpha. So P is less than or equal to alpha because P is 0.0659 and it is less than or equal to 0.1000 or 0.1 or 0.10, however you want to write it. So when P is less than or equal to alpha, we're going to reject and forgive me if I don't write all the details here, but I'm really tired of writing it out. So we're just going to reject the claim that the mean GPA is 2.8. So we've got a couple more examples left. We could definitely have to talk about proportions, right? But they kind of go the same way as far as like, what do I got to plug in? How am I reading this? Am I comparing P and alpha? Yes, you are. So in this case, we're going to do a proportion, two-tailed. We want to test the claim that the proportion of people who own cats is significantly different than 80%. At the 0.1 significance level, we sample 300 people and find that 88% owned a cat. So let's go ahead and state the random variable. The random variable X is whether a person owns a cat. So remember that when we're doing proportions, it has to come from a binomial population. So we need to have that we have a certain amount of trials, right? So we're going to ask 13 people whether or not they own a cat, and then they're going to have a success or a failure. So success would be owning a cat, which I can get behind that. And failure would be they don't own a cat. We also have, it's a simple random sample. Okay, we don't say that explicitly in this problem. We're gonna go ahead and assume it's true. We're gonna always assume that we're taking a simple random sample in the context of elementary statistics. When you guys are out in the world doing statistician things and you're in the wild, it's on you to make sure that you have a simple random sample. While you're under the care of San Jacinto College, we're just going to assume that when we're doing hypothesis testing, we have simple random samples. All right, we have to meet the conditions for a binomial distribution, which is, right, we talked about the n independent trials, yes. Success or failure, yes. Each trial has the same probability of success. We're just gonna kind of take that as granted. And then we also have C, the shape of the binomial distribution needs to be similar to the shape of a normal. So we need to check that NP and NQ are both greater than 5. Well, we can't do that until we plug in NP and NQ. So let's put a pin in that and go on to state our null and alternative hypothesis. And we're going to come back to assumption C in step 2 once we open up our Excel sheet. So remember that the claim is that the proportion is 80%. So our null hypothesis H naught is that P equals 0.8. And then what we're saying is that, well, we think it's different. Not more than, not less than, just different. So our alternative hypothesis is that P is not equal to 0.8. And so that brings us to the two-tailed test, right? So again, one or two tails is determined by the structure and the statement of the alternative hypothesis. So let's establish a level of significance. Oh, one was established for us in the problem. So here we see at the very tippy top, we want to test it at the 0.1 significance level. That just means that alpha is 0.1. And now we want to go ahead and compute our p-value. So let's open up our Excel sheet. We'll see that we can check the assumptions for part C and step 2, and then we can continue on with our problem. All right, so we want to make sure when we're in Excel that we are in our z-test for the proportion. So when we're doing proportions, it's always z-test all the time. It's never not z. P and z, easy peasy. Okay, remember it? Got it. Boom, good. So we need to tell it what our null hypothesis is. And our null hypothesis is p equals 0.8. So let's go ahead and plug that in. We need to tell it what our sample proportion is, our p hat. So our sample showed that 88% owned a cat. So that's 0.88. We need to tell it our sample size, 300 in the problem. And we need to give it our alpha. And alpha was given to us as 0.01. So notice that we get our test statistic, and then right below that we have NP and NQ. So the cool thing about our z-test for the proportion is that it's going to automatically compute NP and NQ. So you can go ahead and look and see that they're both larger than 5. Assumptions met. Let us carry on. So I'm going to grab this, throw it into our notes, and we'll pick it apart. Okay, so here's our output here. And again, as always, we're assuming that the null hypothesis is true, which means that mu, or rather, sorry, P is our mean for this normal distribution here. And what we're saying is that how far away are we from this given P? Well, that's what our test statistic tells us. So our test statistic tells us that we are 3.4641 standard deviations above the mean. So that's like way out here. 1, 2, 3, something like this. So we are 3.4641 standard deviations above the mean, P. The assumed mean. So if our alpha, so remember, this is a two-tailed test. So if our alpha is 0.01, this is kind of an exaggerated thing. If our alpha is 0.01, then this rejection region has area alpha over 2, which is 0.005. That's really small, right? And they both have 0.005, right? Because it's 0.01 split up into 2. So like if you and your friend only had a penny for the both of you, you have to split that penny. You'd have half a cent each. That's really what's going on here, splitting up these two tails. So where does X bar fall into that? Well, according to us, let's look at our two-tail sample. So we've got, So we're doing a two-tail test. So our P value. So this is where it gets kind of hinky because we're talking about P and P hat. And then we also have this P value. This P has nothing to do with the proportion. But I didn't make up that rule. That's just another weird, quirky thing about statistics. So our P value is 0.0005. So X bar is probably like, what do we say? It was like way over here. right? So it's really far away from the mean. It's super likely that we would just randomly get a sample with that high of a p-hat value. So we're going to go ahead and call the people who are claiming 80% liars. We're just like, no, this is so unlikely to happen that I don't believe you with your p equals 0.8. But if I want to do that kind of less snarkily and more mathematically, what I would do is I would just be like, well, p is less than or equal to alpha, folks. So P was 0.0005 and alpha was 0.0100. So I like to have both have the same amount of decimals, just so it's easier for me to compare, because my brain works like this. Is 5 less than 100? It sure is. If I just had this, I'm not so good at making that connection. So if you want to add on extra zeros, be my guest. So we are going to reject the claim that the proportion of cat owners is 80%. And in fact, we're gonna favor the claim that it's higher than that. All right, we've got two more examples. We've got one more example with the proportion that's right-tailed, and then we're going to do another example with just some raw data. So let's look at this. A well-known brokerage firm executive claimed that 80% of investors are currently confident of meeting their investment goals. An XYZ investor optimism survey conducted over a 2-week period found that in a sample of 500 people, 84% of them said that they are confident of meeting their goals. Test the claim that the proportion of people who are confident is larger than 80% at the 0.1 significance level. So we want to state the random variable. So again, the random variable is just whether a single person is confident of meeting their investment goals. So if we're walking down the street and I'm just like, hey man, are you confident of meeting your investment goals? I mean, that would be super awkward, but the guy or gal or whomever, they're either going to say, yes, I am, or no, I'm not, right? So that's success or failure. So that kind of gives you that binomial vibe, puts you in proportion land. Let's check our assumptions. So our data should be from a simple random sample. Again, we're assuming that it is. That's that little college stats class magic that we sprinkle into everything. We must meet the conditions for the binomial, which is we have a certain number of n independent trials. Yes, we do, because we sampled 300 people, and each person, I asked them, are you confident or no? That's a trial. I've got n of them, 300. The outcomes of any trial are success or failure. They're going to say, yes, I am. No, I'm not. Success or failure, check. And then each trial has the same probability of success. This is going to get a little hand washy here. We're just going to go ahead and sprinkle that math 1342 fairy dust on it. And then we also need to check that the shape of the binomial distribution needs to be approximately normal. And the way that we do that is we look at NP and NQ. And we saw that that's happening in the Excel sheet. So we're just going to put a pin in that, dump our data in, and see if that assumption is met. So let's go ahead and just move on to stating the null and alternative. So I want to introduce to you a variation on the notation that we've been accustomed to of late. So the alternative hypothesis, the thing that we want to test, the thing that we want to show, let's go back and see what it is. Test the claim that the proportion of people who are confident is larger than 80%. Okay, so that means my alternative hypothesis should be P bigger than 0.8. That's telling me, first of all, it's a right-tailed test, which I need to remember that. And then the null hypothesis, we're really used to writing our null hypothesis always as P equals blah, or mu equals blah, always equals, equals, equals. But it's justifiable, and we may see in some instances, like in mom, that we may see an option for P is less than or equal to 80%. And that's okay too, because really what happens is we're going to reject the null or fail to reject the null based on our P value and our alpha value. Our P value comes from whether or not we're right, left, or two-tailed test. So really the outcome of our hypothesis test has more to do with how the alternative is stated rather than how the null is stated. And so we just chose a convention where our null is always stated in terms of equality. But regardless of how you choose your convention for the null hypothesis, it doesn't affect the outcome of your test. What did she just say? Anyway, so we want to establish a level of significance, and it's telling us in the problem we want to use 0.10 significance level. So I have a little typo there, and I shall fix it. All right, compute the probability that your sample mean occurs, find the p-value, All right, so let's go make that happen. So we need to dump all of our assumed values and our sample values into Excel. So let's see, what do we have for our null hypothesis for P? So here we had that P was 0.8. So you see again how it doesn't matter if it's less than or equal to. I just need to tell it what P is for the null hypothesis. Okay, P hat, that is our sample. So we sampled 500 people, 84% of them said that they are confident of meeting their goals. So that's going to be 0.84. What if they had said 100 people said they were confident? So if they're giving you the amount of successes and not the percentage of successes, make sure that you put in your p hat as the number of successes over the number of people asked, right? So that's a common theme that we saw in chapter 8. Just a reminder. All right, our sample size was 500. Our significance level was 0.10. So now we get all of our good data, and notice that we can go back and revisit our assumptions. Here we have NP is equal to 400 and NQ is equal to 100. We are in the clear and we can proceed with our hypothesis test. Okay, so remember that we are assuming the null hypothesis is true. So that means that P equals 0.80 is smack dab here in the center. And we want to know how far away is 0.84 from that assumed value of P. Well, again, this is our test statistic. So our test statistic tells us that we are 2.2361 to the right of P. Right, so it's 2.2361 standard deviations above the assumed value of P. So that's going to put us at roughly just like right here, right? So this is 2.2361 standard deviations above P. So that's where we're going to have P hat. Which was 0.84. So before I shade anything in, let's look at our P value. Are we doing a right, left, or two-tailed? So let's go back. I legitimately forgot. We're doing a right-tailed test. So we want to come to our right-tailed test here. So here, I can even, if I wanted to, if I didn't want to fuss with this, well, what's the area? And did X bar land in my rejection region and blah, blah, blah. If I just wanted to straight up be like, look, P is equal to 0.127, okay? Alpha is equal to 0.1000. clearly P is less than or equal to alpha. So I'm going to go ahead and reject the null hypothesis. If you wanted to look at it from an area perspective, you're really just looking at what is the area of this? Well, the area of this is your p-value. And it's equal to 0.0127. Your rejection region has a bigger area. It has an area of 0.1. So the orange region, the rejection region, is bigger in area than the area given in our p-value. So of course that means that X bar must then fall into the rejection region. So therefore we reject the claim that 80% are confident about their investments. Okay, so this is our last example. If you made it to the end of this video, I am more proud of you than I am of me at this point because, wow, this has been really long. So let's just do an example with raw data. And this should feel really familiar to what we did in 8.2 when we had raw data and we wanted to construct a confidence interval based on that raw data. So the work week for adults in the US that work full-time is normally distributed with a mean of 47 hours. That is hilarious. Okay. A newly hired engineer at a startup company believes that employees at startup companies work more on average than most working adults in the US. Okay. She asks 12 engineering friends at startups for the lengths in hours of their work week. Their responses are shown in the table below. Test the claim using 5% level of significance. Okay, first of all, I can already see a huge problem with this. She's asking her friends. Does that feel like a simple random sample to you? I don't think so. I think this problem is whack. But we're still gonna do it just so we can practice. So I'm gonna make a note. We're gonna ignore this requirement. We're just gonna ignore the simple random thing really quick. The population is approximately normally distributed. Let's see, do we have that? Yes, we do. Right there. So we're good to go on that. The population standard deviation is unknown. That's a fact. And so we're gonna use our data to give our sample standard deviation, and that's gonna bring us to using a t-test. The random variable X is just the number of hours worked. I'll just leave it at that. All right, so let's state the null and alternative hypotheses. So the null hypothesis is that the work week is 47 hours, right? So what are we saying here? And then, so that's given in the first line of the problem. Then what we want to show, what we want to test, the thing that will be our our alternative hypothesis is that the mean is actually larger. So that's given right here. So she believes that they work more on average than most working adults. So we're looking at a null of mu equals 47, and alternative of mu is greater than 47. All right, so there's our null and our alternative hypothesis. Next, we need to say, what is our level of significance? So that's going to be in the problem as well. So let's scroll back up. We want to test the claim using a 5% level of significance. So 5% is our alpha. So that's the same as 0.05. So now that we have that, we can go ahead and put this into our Excel sheet. So we are testing for the mean, right? So that's either going to be a z-test for the mean or a t-test for the mean. Since we don't have our population standard deviation, we're going to use a t-test for tough. You don't have the population standard deviation. And so notice here at the bottom, we have this kind of big open area of cells in pink. That's going to be where we're able to input our data. So I want to copy our data. I want to insert it here. And then notice as soon as I insert the data, it's automatically going to compute my sample mean, my sample standard deviation, and my sample size. So notice that it's not going to automatically import it here. So let's go ahead and clear out all this business. What is my null hypothesis? My null hypothesis is that mu is equal to 47. What's my X bar? Well, my X bar is coming from my data. So I need to go down here and I see my sample mean is 52. My sample standard deviation, that's also coming from my data. So I go over here and I see it's equal to 6.75 what? Okay, I'm gonna be lazy. I'm just gonna type in equals B20 because that's where that is located. Hit enter, done. My sample size also comes from here. So it's gonna count how many entries you have. We also see that the problem tells us that the sample size is 12, but might not be lazy. Just steal it from Excel. And then lastly, we need to input our alpha. So we know we're using a 5% significance level. All right, so now we have everything kind of spit out. So let's grab it and digest. So here we have all of our data. And again, we're assuming that the null hypothesis is true. And I want to know how far away I am from, how far away is my sample away from this test statistic? Away from this assumed mu value of 47. And so that's going to be my test statistic here. So remember that this tells me that I'm 2.5639 standard deviations above the assumed mean mu. So 2.5 standard deviations, that's considerable. So it's probably out here somewhere. So this is probably 2.5639 standard deviations away. And so our alpha, our significance level is 5% or 0.05. So that means that our rejection region has to be something like this, right? So it's some area. Because we're doing a right-tailed test, right? Let's look at our null and the alternative. So we want to show that mu is greater than 47. So this is a right-tailed test. Okay, so this rejection region has area equal to alpha, which is 0.05. But I know, looking at my p-value for a right-tailed test, that this area here is 0.0132. So this is a smaller area, which means that X bar lands inside the rejection region. And remember, when you live in the rejection region, you must reject. But again, we could just look at it in terms of P and alpha as well. So remember that we have here that P is less than or equal to alpha because P was 0.0132 and alpha was 0.0500. So is 132 less than 500? Absolutely. So we are going to reject the null hypothesis, right? Or reject the claim that mean hours worked per week is, what was the claim? 47. So that's it. I mean, there's lots of other variations, right? We could have done a left-tailed proportion. We could have done a left-tailed mean with unknown population standard deviation. So you can mix and match these, but it's just important to know, what does your null hypothesis tell you about left-tailed, right-tailed, or two-tailed? What does the standard deviation or lack thereof tell you about a z-test versus the t-test? And when should you use which? And that's really it. So if you made it to the end, you have my respect. Signing off, and I will see you guys when I see you.